Hello everyone and welcome back to the Calculus Fun Room. In today's video we want to take a look at an introduction to polar coordinates. Now initially in this conversation we're going to just discuss the basics of polar coordinates. What is the polar plane? How do we plot points? And then how do we convert between polar and Cartesian? And then finish off the video we'll look at derivatives in the polar plane. And then in the next video we'll wrap up our conversation on polar coordinates, looking all about calculus of polar curves. We'll talk about area and other things of that nature, other fun stuff. Now to just stop for a second, this is not a history class, but to give a little bit of perspective here. Around 1630s, René Descartes had invented the Cartesian coordinate system. Now of course, René Descartes did not call his coordinate system after himself. Right? He invented a coordinate system, and later, after his passing, it was named after him. Now, if we think about what we do in this coordinate system is we label a point, a location in the coordinate system in terms of a horizontal and vertical distance, right? So my ordered pair tells me I would move, horizontally some distance, x units, and then I would move vertically some distance, y units. Of course, I don't have to do x and y first, right? I could always move my vertical y distance first and then my horizontal x distance next. But I have a horizontal and vertical distancing, directed distance way in which I address a particular point within that plane. And what's actually really amazing about the invention that René Descartes had here, his coordinate system, is before that, math was really kind of thought of in two different buckets, if you will. So like geometry, visualization of geometrical images and the study of those was pretty separate from, algebraic study. And I don't just mean algebra classes, but, study of equations and things of that nature. René Descartes' invention it really brought together the two subjects to what we see today. I mean, I think of a calculus course. I can't imagine learning calculus without being able to look at the graph, right? And when we talk about a rate of change of a function, and we visualize that as a tangent line, right? Slope of a tangent line. And when you take an algebra course, you learn about, the square function, and we graph them, and we see lots of really unique relationships by connecting the algebra to the visualization of it, the graph. So René Descartes this was a groundbreaking invention. This was really pretty amazing in the early 1600s. Now, couple decades after that, Sir Isaac Newton had invented a couple other coordinate systems, and one of them being the polar coordinate system. And the difference between the Cartesian and the polar coordinate system is just how we address a point. I actually don't want to draw it that way yet. So typically in a polar coordinate system, we think of having a pole, which is the origin, and then we have our polar axis. And what we typically do within this system is we think of plotting a point in the plane, and we would address that point with an ordered pair r theta. And what that ordered pair represents, I'm going to pick a different color here. So the theta would be the angle measure that we rotate off the polar axis. So that's theta. And then r is the directed distance from the pole. Now if we think back to what you would have learned about in a trig class, the convention is that if theta is positive, then that means we rotate counterclockwise off the polar axis. And then if theta is negative, we rotate clockwise. So, for example, let me throw another grid down here. If we're moving off my polar axis and I rotate to pi over 2, right? That is a counterclockwise rotation off the polar axis. If I rotate to negative pi over 2, right, that is a rotation in a clockwise direction off of the polar axis. This angle measure of negative pi over 2 is equivalent to the angle measure of 3 pi over 2. So what I want to do here is I went online, I did a quick Google search of polar axis, and I found a picture. So on this polar graphing paper, we can see typically what we might see with a unit circle. We have a label all the way around, right, of all the angle measures we can have in one rotation. Now, point out to you on this graph paper, I don't see the negative angle measures listed for me, right? I would need to count around to figure those out, but here is a gridded graph paper for polar. Now, some pages that you find online when you do a search don't have those angle measures labeled for you on the outside of that circle. There's just a whole bunch of concentric circles with radial lines. First, let's just get a little bit of practice plotting points and refamiliarizing ourselves with this topic of graphing in the polar plane. So let's just plot a couple points here. Let's say point A, I want to plot, let's say 2 comma, 2 pi over 3. All right, now again, looking on my gridded paper, I see where 2 pi over 3 is. If you think about pi over 3 is 60 degrees, so 2 pi over 3 is 120, so I can see 2 pi over 3 up here, where 120 degrees is. So if I'm looking at my pole, my origin, right, here's my polar axis, theta equals 0 radians. So 2 pi over 3 is rotating along to that line. So here's 2 pi over 3 here. That was a sloppy rotation. So what we want to do is we want to follow along the terminal side of that angle measure, and then we want to move 2 radial units along that line. So here's 1 radial unit, and here's 2 radial units, right? Here's 3, here's 4, here's 5, right? So all of those concentric circles show me my radial distance along the terminal side of that angle theta. So let me erase all these other ones I don't want. And here is the point that lies 2 pi over 3 radians from the polar axis and is a distance of 2 radially from the pole. Let's do one more, and then I'll let you do a couple for me. So let's say point B, we want to plot the point 5, let's say negative 5 pi over 6. Now with my gridded graph paper, right, the disadvantage is I don't have the negative angle measure, but that's not really that big of a deal. What I like to do, what I teach my classes is, I like to count around as we move around the circle. So first of all, this is negative. I know I'm going to be moving in a clockwise direction. And I know that pi over 6 is, what is that, 30 degrees, right? So if I did pi over 6, 2 pi over 6, 3 pi over 6, so 3 pi over 6 is pi over 2 from the polar axis. So again, here would be pi over 6, here would be 2 pi over 6, and here would be 3 pi over 6. And then I would have 4 pi over 6, and then I would have 5 pi over 6, and then I would have 6 pi over 6. Of course, these are negative rotations that I just mentioned there. So I kind of like to count my way around as how I personally like to do that. So I can see that here was the negative 5 pi over 6. There was the terminal side of that angle measure. I'm going to come back and erase the rest of those. So here's negative 5 pi over 6 right here. Now that I've located negative 5 pi over 6, what I want to do is move a radial distance of 5 along that line. And I've made that line really solid. Let me make it look a little cleaner. So I'm going to have, let's see what I got, 1, 2, 3, 4. So here's the point B, where I would lie on the terminal side of the angle negative 5 pi over 6 and lie 5 units from the pole. All right, so I want you to do a couple for me. I want you to plot point C, and point C I want you to be at 1, comma 3 pi over 2. And then point D I want you to be at, let's say, 1 comma negative pi over 2. So pause the video for me, and I want you to plot those 2 polar points, and when you're done, unpause and we'll look at those together.
So let's use what we just discussed and plot a couple points here, get a little bit of practice plotting points in the polar plane with our polar graphing paper that we have. So let's suppose that I want to graph, and let's call it point A. Suppose I want to graph the point 3 comma 7 pi over 6. So again, the way that I think about this, right, here's my polar axis, and because this is positive angle measure, we're going to rotate counterclockwise, and we can see on our graphing paper right here 7 pi over 6, right? So we're rotating to that point, and obviously that line that I just drew is not a plot of my part of my point. So here's the terminal side of angle measure 7 pi over 6, and I want to plot 3 radial units from the pole. So I'm going to go 1, 2, and then 3. Here's my point A that we're going to plot. So let's say B 4 comma negative 5 pi over 6. All right, now my graphing paper, if I go from my polar axis, my graphing paper doesn't have negative angle measure. So I'm going to count backwards. So remember, pi over 6 is 30 degrees, right? So going to this radial measure, right, that's 1 pi over 6. Then I'm going to have 2 pi over 6, which is 60 degrees. Then I'm going to have 3 pi over 6, right? 3 pi over 6 is negative pi over 2. Right? So then I have 4 pi over 6 and then 5 pi over 6. So it turns out negative 5 pi over 6 is coterminal with 7 pi over 6. So I'm going to move along that same radial line, and I'm going to go a distance of 4, which would be here. So let's do a third point. Let's say we do 2 comma negative 5 pi over 4. So again, I got to count backwards. And 5 pi over 4, right, is a multiple of pi over 4. Pi over 4 is 45 degrees. So I'm going to go along the outside. So I have, here's 1 pi over 4. And then we have 2 pi over 4. So again, negative 2 pi over 4 is negative pi over 2. And then we have negative 3 pi over 4, negative 4 pi over 4, obviously is negative pi, and then we have negative 5 pi over 4. So we're coterminal with the angle measure of 3 pi over 4, and then we want to go 2 radial units along that angle, and that's going to put me right here, and there is point C. When we're plotting in the polar plane, we can also have the convention that r is negative. It seems a little bit weird. R is a radius. A radius should be positive, but we're going to go ahead and accept the convention that r is negative. So in theory, let me just scroll down for a second. Let's suppose we have the the ordered pair r theta. So if I think of theta for this example as being a positive angle measure, here would be the point positive r. The point negative r would reflect me through the pole. So this is basically like a rotation of 180 degrees, pi rotation away. Negative r theta is the angle of r and then theta plus pi. Of course, we could always think of subtracting pi to get to that same point as well, I think, due to the periodicity of trig functions and our angle measures. So basically, the way I like to think about this, I'll rotate to the angle theta, and instead of moving in a positive direction, I'll move in the reflection through the pole. So if I come back up here and let's plot the point negative 3 of 5 pi over 6. So first, what I like to think of, as I mentioned, I'm going to rotate to 5 pi over 6. So I have on my gridded graph paper the positive 5 pi over 6 already labeled here. Now if I was plotting the point positive 3, I would move along that line and go 1, 2, 3 and plot the point here. But because the r is negative, we're going to move through and we're going to reflect through the pole here. And we're going to move 1 to negative 3 units. And there is point D. So let's do one last point. Let's say point E, and let's look at negative 3 comma pi over 6. So I'm going to go to theta being pi over 6, and because my r is negative, I'm going to reflect through the pole onto this side, and I'm going to move a distance of 3. 1, 2, 3. So as it turns out, point E and point A are equivalent. So this last point, the last ordered pair that we plotted, brings up the point that an address or a label in the polar plane is not distinct. So we have point A and point E representing the same plotted point in our plane. So we have two different labelings, two different ordered pairs that address the same point in the plane. When you think about this for a moment, if we plotted points in the xy plane, let's say I plotted the point 3, 1, that is a distinct labeling. There is no other way to get to that point with a different address, if you will, no other ordered pair. So the polar plane, again, due to the periodicity of as we rotate 2 pi, then we go to 4 pi and 6 pi, right? We just end up repeating ourselves, and with the convention of negative angle measure and negative r's, we have infinitely many ways we could represent any point in the polar plane. Now that we've discussed plotting points, the next thing we want to look at is how could we convert between polar ordered pairs and Cartesian ordered pairs. If we think about laying on top of each other a Cartesian point xy and a polar point r theta. Now for our Cartesian point, our xy labeling is a horizontal and vertical directed distance. And then our ordered pair, r theta, is a radial distance and an angle measure of theta. So there's some connections here, right, with right triangle trigonometry. So the first couple connections we can make, let's say that sine of theta is opposite over hypotenuse, and that tells us that y is equivalent to r sine theta. So in other words, if we have the r theta ordered pair, we can then convert and find the y Cartesian coordinate. And then very similarly, cosine of theta is adjacent over hypotenuse. So that tells me x is r cosine theta. These two equations convert from r theta to Cartesian. How do we go in the other direction? So a couple other relationships that we can see up here. We have Pythagorean's theorem, x squared plus y squared equals r squared. So when we look at that equation, if we have the x and the y coordinate, then we can find the polar point. Now if I plugged into the Pythagorean theorem there, I would end up solving for r. So if I square root both sides, I technically have a plus or minus the square root of x squared plus y squared equaling r, and it is okay, right, for us to keep the negative. We just discussed a couple minutes ago that we can have r's that are negative in our polar plane. Now the other connection we have is that the tangent of theta is opposite over adjacent. So if I take the inverse tangent, the arctangent of both sides, again, in this scenario, if I have the y and the x coordinate, then this allows me to find the theta value. So r being plus or minus square root of x squared plus y squared, and theta being inverse tangent of x over y, this is going to help me convert from the xy to the r theta. Let's take a look at an example where we want to convert from polar to Cartesian. So those first two conversion equations we had was x equals r cosine theta and y equals r sine theta. So for this particular example, my r is 2 and my theta is pi over 3, and then y would be 2 sine of pi over 3. Now, I always forget what those values are. I never memorized them. So you might pull up, you could pull up a unit circle and find what those values are. I'm going to go ahead and remind myself. So I have a 30, 60, 90 triangle, and I would label the sides as 1, 2, and square root of 3. So let's see, pi over 3 is 60 degrees, so I'm looking up at this angle. So cosine is adjacent over hypotenuse, which would be 1/2. I'm going to have 2 times 1/2 as my x-coordinate. And then the sine of 60 degrees is opposite over hypotenuse, so that's going to be square root of 3 over 2. So my xy Cartesian point is going to be 1 comma root 3. I just want to visualize real quick and do a rough little kind of check that my conversion seems legitimate. So if I plot the ordered pair 2 pi over 3 in the polar plane, pi over 3 is about 60 degrees. So I'm along that terminal side of the angle of 60 degrees, and then I'm going to move 2 units. So, let's say here's 1 radial unit, let's say here's 2 radial units, or a sketch here, right? So there's 2 comma pi over 6. And then the xy coordinate would be 1 root 3. So looks like 1, and root 3 is about 1.4-ish, I believe. So there would be root 3. So that seems reasonable that we didn't make any errors in our conversion there. And we could do some more examples here where I convert from polar to Cartesian. I don't want to do that. It's really the same plug and chug process where the theta is negative or r is negative. It's really going to be the same work that we do there. So let's go in the other direction. Let's suppose that we're going to convert the Cartesian point, let's say -1, 1, and we want to convert to polar. Now the conversion equations that we wrote up top, we had theta was inverse tangent of y over x, and then r was plus or minus the square root of x squared plus y squared. So how do I know whether I choose the positive r or the negative r? Well, we'll discuss that in a moment as we work through this example. I'm going to plug in the y and the x for my theta. I have inverse tangent of, this is going to be what, 1 over -1. So I have the inverse tangent of -1. Now if I pull out my calculator and I do arctan of -1, I'm going to get negative pi over 4 as the output. Technically, there's infinitely many angles that I can take the tangent of to get -1 due to the periodicity of our trig functions, but this is what the calculator would give me. So let's go with this for the moment, and let's come back and talk about some other options. So if we plug into the r conversion, my x was -1, I square that. My y is 1, I square that. So I get r is plus or minus the square root of 2. Which r do I choose there? So I'm going to do the same thing we did up in that problem above. I'm going to plot this point. So the Cartesian point -1, 1 is going to lie in quadrant 2. Now if we go with the calculator's theta of negative pi over 4, right, that puts us a rotation of -45 degrees. So in order for us to get into quadrant 2, we're going to have to choose the negative r. So one possible conversion into polar is -√2 comma negative pi over 4. Now when we look at this ordered pair here that we have, -1, 1, we notice that we could rotate to 3 pi over 4. If I went to 3 pi over 4, I would then need to choose positive root 2. So again, we have 2 different ordered pairs that can represent that same Cartesian point, and the reality is we have infinitely many ordered pairs as we add or subtract to pi and make the r positive or negative. So usually there's a pretty typical question when I'm covering this in my class, which is why does the calculator only give me negative pi over 4? And that's a great question. Let's delve into that for just a moment. If we think about when we develop inverse functions in a algebra course or even a trigonometry course, if we graph the tangent function, we see roughly something like this. And pi over 2 and negative pi over 2 are my vertical asymptotes. Tangent is sine over cosine, so when cosine is 0, I get division by 0. Those are my asymptotes, right? And then the tangent function repeats itself in its periodic manner. Now, in order for me to take the inverse, right, whenever I do the inverse function, I reflect the graph over the line y equals x, and it creates the inverse tangent function as we know it. So pi over 2 and negative pi over 2 are horizontal asymptotes on my inverse tangent function. So we can see that the outputs for inverse tangent are going to live between minus pi over 2 and pi over 2. And that is why we got negative pi over 4 out of our output. Because when x is negative 1, my output is negative pi over 4. So when I scroll back over here, we were taking the inverse tangent of negative 1, and we get negative pi over 4. So again, my calculator is going to be limited to producing outputs from minus pi over 2 to pi over 2. It's usually most homework problems in textbooks. When they have you convert from Cartesian to polar, they'll say give 2 ordered pairs in the polar plane. And this illustrates how we would accomplish that. All right, next example I want to look at is how we would graph a polar equation. Now, I do want to come back to conversion. The other type of a conversion I want to discuss is how would we convert an equation between both forms, right? So how could we convert this polar equation that we have here back to a Cartesian and vice versa? But before we do that, I just want to take a look at graphing. Now, ultimately, we're going to lean on technology to do graphing for us, because in order to look at some really cool, fun stuff, the graphing by plotting points would be extremely tedious. But to understand where these graphs come from, we always want to start by plotting points. So let's go through that process for this relatively simple equation to see what that would look like. So just like I've been plotting points, r theta, I always rotate the theta first, then move out the distance r. Plot a grid. And for some particular theta, I'm going to find my r value. So let's just go ahead and start with theta equals 0 here. So if I plug theta equals 0 and cosine of 0 is 1, and I get an r of 2. So if I plot that point, I'm sitting right here at r equals 2. So if I'm plotting points by hand, I have to pick angles of which I can find exact values. So the next angle I would find an exact value of is 30 degrees, right? Pi over 6. So if I pick pi over 6, if I look at my reference triangles or I look at a unit circle, I can see that the cosine of pi over 6 is 1 over, square root of 3 over 2, and that gives me root 3. If I plug that in a calculator, that's about 1.7. So I'm going to go on my line that I just drew, my angle measure, and I'm going to go about 1.7. Now keep in mind, these angles that I just drew aren't really a part of my graph. So then I'm going to do pi over 4. So cosine of pi over 4 is 1 over root 2, and that's going to give me approximately 1.4. So 1.4 roughly there. And then let's see, pi over 3, so 60 degrees. Cosine of pi over 3 is 1/2, so I get 1. So moving along pi over 3, I get a radial value of 1, which is roughly about there. And then the next angle for me to pick is pi over 2. Cosine of pi over 2 is 0, and so I get 0. So again, keep in mind, I'm looking along the angle measure of pi over 2 here, and my radial value is 0, so I'm sitting on the origin. So then I would continue, right? So my next angle measure I would look at would be this 2 pi over 3 here. So let's say I pick 2 pi over 3. So 2 times, and the cosine of 2 pi over 3 is negative 1/2. So I get a value of negative 1. If you think about this for a moment again, right, so here's 2 pi over 3, but a r of negative 1 puts me through the pole in the other direction. So there's a r of negative 1. So I'll continue. Let's pick 3 pi over 4. right? Picking 3 pi over 4. So cosine of 3 pi over 4 is negative 1 over root 2, and so that gives me roughly negative 1.4. And that's about right here, negative 1.4. And then the next one I'll look at is 5 pi over 6. And that is negative root 3 over 2 for cosine. So again, that's going to be about negative 1.7. So I'm going to be about negative 1.7 as our value. And then when I get to pi, cosine of pi is negative 1, and I get negative 2. So here is pi, and then the r is negative. So that puts me right back where I started here. All right, now if I were to continue plotting, so let's suppose I picked 7 pi over 6, I'm going to get an r that's negative, and it's going to put me right back at the same point where I had pi over 6. And I would get this repetition, so my graph starts here and moves around in that direction. I should be seeing something that's a circle that looks roughly like a circle with my somewhat precise plotting. If we're going to lean on technology, let's take a look at a TI calculator real quick. So I would want to hit the mode key, and I would want to change to to polar mode. And then I always make sure that I'm in radian mode here and not degree mode. So just pay attention to that. Now when I hit the y equals key, notice we have r equals f of theta. So I'm going to go ahead and type r equals 2 cosine, and then again I'm going to hit my theta button here, my variable button, and when I graph, let's see what happens when I graph. I'm going to do zoom decimal, zoom 4, and there's my circle. Now I don't know if you noticed, but it actually traced the circle twice. In fact, if I hit trace and I just hold my button down, we can see from 0 to pi, and then from pi to 2 pi, it's tracing again. Now, that doesn't always happen, but in this particular case, the cosine of theta, r equals cosine theta, only needs 0 to pi. Now, something else to point out to you, right? When I hit trace, I can always punch in a number like second pi over 2 and have the calculator jump me right to a particular point there. Something else that's kind of unique you'll notice on the TI is if I look down here as I plot points, the theta value I plugged in was pi over 2, and it's telling me the xy coordinate. So what the calculator is doing as it graphs is it's thinking of theta as a parameter, really, and it's giving you for the theta value what is the xy Cartesian point. So if you want to plug a theta in and get the r value, you have to go to the table. So I'm going to do second graph and go to the table, and you can see here it's going to spit out for me the r values. And then one other thing I want to mention to you while we're here, if I hit the window key, right, here's where I could change theta min and theta max, and then how often I plot a theta. Usually this is around 0.1 or 0.05 is good. And then my x min, x max, y min, y max are really referencing the x axis and the y axis. Let's take a look at a couple very basic equations, and then I want to pull back to the technology and look at some really cool equations. So one really basic equation you typically will see is r equals a constant. So what if I had r equals 5? Now if we take a look at plotting points here, right, if I'm building a table, right, and I'm picking theta values and plotting r values, if I pick theta equals 0, my r is 5. If I pick theta equals pi over 4, my r is 5. If I pick theta equals pi over 2, my r is 5. So it doesn't matter which theta I pick, my r is always a radial unit of 5 away. So I'm really graphing a circle in the polar plane. So notice how beautifully simple that equation is, right? I mean, if I wanted to graph a circle in Cartesian, right, that would be x squared plus y squared equals 5 squared for a circle centered at the origin. So you can see the polar plane has some advantages that some graphs that we plot will have a much cleaner looking equation. Now let's suppose I wanted to plot the equation like theta equals pi over 4. And again, if I think about plotting some points, This is basically saying theta has to always be pi over 4. So if I pick theta equals pi over 4, what is r going to be? It's going to be anything that it wants to be. So this graph is making me stay at pi over 4. If I'm going to satisfy that equation by plugging in a point, the theta has to be pi over 4. And because the r is missing, that says r could be anything that it wants. R could be 1, 2, 3, 5. R could be e squared. R could be -1, -3. Theta equals a constant is actually a line, and the theta value is representing the slope, right? Is connected to the slope in this case. So these are two unique types of equations. R equals a constant is a circle centered at the origin with radius r, right? R equals 5 in that case, and then theta equals pi over 4 is a line. Let's take a step back and talk about converting equations. Now remember, we had our conversion formulas: x equals r cosine theta, y equals r sine theta, and then we had theta equals inverse tangent of y over x. And remember, that came from tangent of theta being y over x, and then we had the x squared plus y squared equals r squared. So let's suppose we had the equation r equals 5, right? So we want to convert the equation r equals 5 polar to Cartesian. So we have that r squared is x squared plus y squared. So what I'm going to actually do in this case, I'm going to square both sides of this equation. And when I square both sides of this equation, I get r squared equals 25. And then from my Pythagorean theorem, r squared is equal to x squared plus y squared. And that's equal to 25. So in this case, to convert from polar to Cartesian, we're trying to connect to one of our 4 conversion equations. In this case, the Pythagorean theorem, x squared plus y squared equals r squared. So in order to connect to that, we had to square both sides of our equation to be able to plug in or replace for r squared. For the next example, let's come back to that problem we had graphed in the very beginning, r equals 2 cosine theta. So if I'm trying to convert this polar equation back to Cartesian, this one's a little trickier, but what I'm going to do in this case is I am going to, right here, I have r cosine theta equals x. I could wish I had an r cosine theta on the right hand side, and I can make that happen quite easily. So I'm going to multiply both sides of this equation by r. Now that's really sloppy notation, but I'm multiplying the left-hand side of the equation by r, and I'm multiplying the right-hand side of the equation by r. And again, the advantage, I'm trying to match my conversion equations. R cosine is equal to x. And then on the left-hand side, I have the r squared, which is x squared plus y squared. So here would be my Cartesian version of the polar equation r equals 2 cosine theta. R equals 2 cosine theta was a circle that looks like this, and the circle was not centered at the origin. Our 2 was our furthest distance from the pole, so the center is 1. And we could, I'm not going to take the time, but we could convert our equation here to, x minus h squared plus y minus k squared equals r squared. That's our standard form for a circle in an algebra class. But that would require me completing the square, and I don't want to bother going through that. In pretty much every textbook, if the question, homework problem is saying convert the equation r equals 2 cosine theta to a Cartesian form, then what I boxed in and starred there is a sufficient answer. Now let's come back and take a look at that last example, which was theta equals pi over 4. Remember, I'm trying to match the equations that I have above. Now if I go directly to theta being inverse tangent of y over x, then I'm replacing my theta with inverse tangent of y over x. Now remember, this equation that we graphed here was a line at an angle of pi over 4. And obviously, inverse tangent of y over x equals pi over 4 does not look like the equation of a line y equals mx plus b. What I'm going to do in this case is I'm going to take the tangent of both sides of this equation. So if I take the tangent of the left-hand side, tangent of inverse tangent, those cancel each other out, and then I have tangent of pi over 4. I know the tangent of pi over 4 is equal to 1, so I really have y equals 1 times x as my Cartesian equation. And there's a couple other really cool shaped graphs that would be very tedious to sketch by hand. With technology, we can do this very quickly. So if I graph r equals cosine of, let's do 2 theta, and some textbooks call this a rose or a flower or petals. So we can see we get like 4 petals on a flower here. Now, if I graph r equals cosine 3 theta, we're going to get 3 petals. So for cosine of n theta, if n is odd, I get n leaves, and if n is even, I get 2n. I get twice that. Right? So when I had cosine 2 theta, I actually got 4 leaves there. Now, if I do sine of, let's say, 5 theta, right, I'm going to get really the same relationship. Now I want to turn off my first graph. So if I graph, that is sine of 5 theta. So notice the leaves are oriented slightly different. And if I go back to y equals, and I'm going to turn that graph on. And in fact, you know what? Let me increase the radius here. So I'm going to insert let's say a 4 in front of both of these, just so I can make those leaves a little bit longer. Right, so the red one is 4 sine theta. So we can see the petals just begin at a different place as theta varies around the graph. And I'm also noticing something here unique that I'll mention to you. If I go, notice how the sine graph looks a little jaggedy. If I go to the window, that's my theta step. So if I make my theta step a little smaller, let's say like 0.05, let's say. Let's see what happens then. I get a little bit better resolution, right? So it's plotting more points. Now, a couple other really cool looking graphs. Let's look at 1 plus sine theta. And this graph is what we call a cardioid. It looks kind of like a heart. It's upside down the way that I did this. If you did 1 plus cosine theta, it's just a rotation of 90 degrees and will lie kind of along the x-axis. Now, if we do a couple unique things here, if I think of this as a plus b sine theta, if I make the coefficient of the trig function bigger than the 1, we get a little loop inside of that cardioid. And if I make the a, again, if I think of this as a plus b sine theta, if I make the a bigger, it kind of pushes that dimple out. It's no longer really a cardioid, is no longer really a heart. So those two different types of equations, the petaled rose or the cardioid, and the couple versions of the cardioid, are really unique graphs. Those are real classic types of polar equations that you might deal with in your calculus textbook or your calculus class. The last conversation in this section will be to consider tangents to polar curves. And just like we did with parametric equations, I mean, if I draw that cardioid that we just looked at, when I'm considering tangents in the polar plane, I still want to think in terms of dy dx, delta y over delta x, because if I'm thinking of the slope of the graph, slope of a tangent, I'm still thinking in terms of rise over run, or delta y over delta x. So to find delta y over delta x or dy dx, what we really are going to do is convert into a parametric form in essence. So what we're going to do is we're going to regard theta as the parameter, and we're going to think of this as parametric. I'm going to think of theta as a parameter. Think of theta as a parameter. So in other words, what I'm going to do is convert, and I'm going to use the equation, x equals r cosine theta and y equals r sine theta. Now we had talked about in the prior video that once I had like functions of t, then I'm going to use dy dx being dy dt over dx dt, but in this case our parameter is our theta value. Let's take a look at an example of how we would apply this concept. So I want to come back to the cardioid that we were graphing just a minute ago, and the cardioid looked something like this. And let's say we want to find the horizontal and vertical tangents. So we can see when we look at this graph, we're going to have a couple of those. Looks like, if I switch to orange here, looks like there's going to be a horizontal tangent here, one here, one here. Looks like we're going to have vertical tangents here and here as well. So let's see what that would look like, or how we would do this process. Now remember, what I have up in this orange box is that I want to convert. So I'm going to convert x equals r cosine theta. Now in this case, our r equation is 1 plus sine theta. So I'm going to do 1 plus sine theta and then times cosine theta. And then my y equation, I'm going to convert y equals r sine theta. So I'm going to have my r times sine theta. Now again, my derivative wants me to find dy d theta over dx d theta. So let's go ahead and take each of those derivatives. So what is dy d theta? So I'm going to do a product rule. So I'm going to have derivative of the first times the second plus first times derivative of the second. And then my dx d theta, I'm going to have, what am I going to have? Dx d theta, making sure I'm looking in the right place. I'm going to have derivative of the first times the second plus the first times derivative of the second. Now I might be able to clean those up, I'm not sure. I will do that in the next step. So my dy dx derivative is going to be, again, our parametric form, dy d theta over dx d theta, which we already found those equations. So my dy d theta, so I'm going to go ahead and distribute and multiply things out. So, cosine theta sine theta. If I distribute the cosine over here, I'm going to get another cosine theta sine theta. So I'm going to actually have two cosine theta sine thetas, and then cosine theta times 1. And then in my denominator, let's see, cosine theta squared, I'm going to get negative sine theta squared, and then negative sine times 1. All right, so for the horizontal tangents, I'm going to set the numerator equal to 0. Right, so the only time a fraction is equal to 0 is when its numerator is 0. So I'm going to take the numerator of our derivative. I'm going to set that equal to 0, and I'm going to solve that equation. Now in this case, it looks like I can factor. So let's factor out a cosine theta. We're left with 2 sine theta plus 1. I'm going to set each of those factors equal to 0. So let's see if the first equation is cosine theta equals 0. Let's take a look at that solution. Now, up until this point, I've been working through the reference triangles and finding exact values in that manner. Let's just go ahead and be a little more efficient, and let's look at a unit circle. Alright, so I have a unit circle here, and I'm looking for where cosine is 0. And then remember, the cosine is the x-coordinate, and the sine is the y-coordinate. I can see cosine is equal to 0 at pi over 2 here, and then cosine is equal to 0 at 3 pi over 2. So I'm going to get theta equals pi over 2, and then 3 pi over 2. And then this equation is, where is sine theta equal to negative 1/2. So sine is going to be equal to negative 1/2 here, which is 7 pi over 6. And then it's going to be equal to negative 1/2 here, which is 11 pi over 6. So I'm going to have theta being 7 pi over 6 and 11 pi over 6. Now when I come back up and look at my graph, let's take a look at where my horizontals would be. So I'm getting 4 values of horizontal, and I don't remember seeing 4 horizontals on my graph, right? I definitely don't have 4 horizontals on my graph. So we're picking up an extraneous value, and we'll come back and look at that here in just a second. So I'm bringing my calculator back up. I'm going to hit trace, and the first value we found was pi over 2. Then we can see here's theta equals 0. Theta equals pi over 2 should be along here, which makes sense, but let's go ahead and trace and do second pi divide by 2 and hit enter, and there is that one value. And then the next value we had was theta equals 3 pi over 2. And there's a point where we have a corner on the graph. So the tangent really isn't horizontal there. Remember that at a corner, a tangent is undefined. The derivative is undefined. And we'll come back and look at that in a minute when we look for the vertical tangents and see if we're getting division by 0 there. So let's see, then our next one was 7 pi over 6, and I can see there's the horizontal tangent, and then the last one was 11 pi over 6, and we're going to see that other horizontal tangent. So really the horizontal tangents are going to be pi over 2, 7 pi over 6, and 11 pi over 6. Now let's look for the vertical tangents. Now remember, the vertical tangents are going to come from division by 0, so let me scroll back up and look at my derivative. So I'm looking at where I'm going to have division by 0. So I'm going to set cosine squared minus sine squared minus sine. So cosine squared minus sine squared minus sine equal to 0. Now this is a little trickier of an equation to solve here. I don't have anything that can factor, but an identity does come to mind. It looks like if I write cosine squared as 1 minus sine squared theta, then I end up getting, all of sines in my equation. So see, I end up with minus 2 sine squared of theta minus sine theta plus 1 equal to 0. And I'm going to divide everything by negative 1 because I prefer to have a leading coefficient of 2. And it looks like that's going to factor. So I have 2 sine theta times sine theta, and then the factors of 1 and 1, and then I want a positive sign in the middle, so I'm going to have a plus and a minus. So we're going to set equal to 0. So if I set this factor equal to 0, solving sine theta equals 1/2, and set this factor equal to 0, I got sine theta equals negative 1. The sine is 1/2 is going to be at pi over 6 and 5 pi over 6. I'm going to get pi over 6 and 5 pi over 6. And then I want to know where the sine is negative 1. So the sine is negative 1 is going to be, and there's our 3 pi over 2 that we were getting over here where we had that corner on that graph. So it looks like most definitely the 3 pi over 2 is where my derivative is undefined in that case. We have pi over 6 and 5 pi over 6 is where I'm going to have those 2 vertical tangents that we drew here and here. Okay, so this really covers everything that we would want to cover in this section. Just one other concept here. For this problem, we were finding where the tangent was vertical or horizontal. Let's suppose the problem said, find the tangent at pi over 4. All right, so we can see, here's pi over 4, and at that point, the tangent isn't horizontal and vertical, but we might have been asked to find the slope at that point. So if we come back to our derivative formula that we have here, we're literally just be plugging in theta equals pi over 4 into that derivative and getting the slope out of that formula. So this really covers everything that we would cover in an introductory section of polar graphing, and in the next video we're going to take a look at more examples of calculus with polar curves. Look forward to seeing you then.